So our first speaker is going to be Johnny Ureta Berrena. He's a PhD student from Ikerlan, which is a research center in the Basque Country in Spain. And he's going to be telling us all about his latest research, which he's titling Towards Active Participant-Centric Vertical Federated Learning. I think this is a very interesting piece of work and looking forward to learn all the details. So the floor is yours, John.
Thank you for the introduction, Javier. So I will go ahead and share the screen. Well, so as Javier has said, I'm Johnny Dureta, and I'm a first-year PhD student at Ikerlan Technology and Research Center. So today I'll be presenting our latest work in federated learning, which is entitled Towards Active Participant-Centric Vertical Federated Learning, Some Representations May Be All You Need. This work is the result of a collaboration with the University of the Basque Country. Before getting into the technical part, I would briefly like to introduce what Ikerlan is. So Ikerlan is a research center that is located in the Basque Country, as Javier has said, in the north of Spain. And we do have offices and labs in different cities, such as Bilbao, Hernani, and Mondragon. But Ikerlan is part of the Mondragon Corporation, which is a corporation that is composed by 268 companies and has more than 73,000 employees worldwide. But what do we do in Ikerlan? Well, so we do have three main lines of work that are digital technologies and AI, embedded electronic systems and cybersecurity, as well as energy and mechatronics. So I'm part of this first section, and in here we do have two main subgroups that are distributed and connected intelligence and artificial intelligence and data. Me, myself, I'm developing my PhD in the AI team, but as you can see, we do have some other teams that work in closely related topics. So with that being said, let's get into the technical part. This is the index of today's presentation. So I would like to start by introducing vertical federated learning and trying to clearly define the problem that we are trying to tackle in our work. After that, I will talk about our proposal, APC-VFL, which stands for Active Participant-Centric Vertical Federated Learning. And I will close the presentation with some experiments that we have performed, the results that we have obtained, and conclusions and future work. Well, so let's get started. So I won't get into what federated learning is, nor why it should be used, but I will start by talking about different types of federated learning, right? So these different types can be defined based on the data partition between participants. So we can either have horizontal federated learning, which is the typical one. Most of the people do research in this field, but vertical federated learning also exists, and I will focus on this second one. So vertical federated learning, as the name shows, means that we have a data set that is vertically partitioned between participants, as we can see in this figure over here. So that results in a scenario where different participants have distinct features about some common samples. Since the data set is vertically partitioned, we do also assume that there's a single participant that has access to the labels, and this participant is known as active participant. But it is unable to train a good classifier to predict those labels on its own. And because of that, it does require some help. And the ones that help the active participant are the passive participants. And this is pretty much the vertical federated learning setup. And taking this into account, I would like to start by explaining a classical vertical federated learning approach, which is a vertical split NN. So to understand how it works, let's assume that we have this scenario over here, where we have three different participants. So vertical split NN requires each participant to have a local encoder or a local feature extractor, and then the active participant must also have a classification header. So how does the forward pass work? Well, each participant must get the embeddings, the representations of the batch, and send them to the active one. The active will aggregate them all, ideally by means of concatenation, and then it will perform the predictions using the classification header. As we have previously defined, the active participant does have access to the true labels, and because of that, it will be able to compute the loss and update this classification head with regular gradient descent. After that, it will have to compute the gradient with respect to each one of the local outputs and send it to the corresponding participant. On that way, we can also update these local feature structures. So even though this is like a pretty logical approach to tackle or to face this BFL scenario, this vertical split NN and the other classical BFL algorithms have two main issues. Those are that, first of all, they do require to exchange a lot of information between participants for the training. Because as we can see here, for example, per batch, each participant needs to send the representations of the data to the active participant, and then it does also need to get the gradients. And then another issue, which may not be that straightforward to see, but is a really big issue, is that they are limited to the usage of aligned data. So what is aligned data? Well, we see that a sample is aligned among participants if and only if every participant has information about it. So for instance, if these three participants were three hospitals, we will say that a sample, that is a patient, is aligned among them if that patient has visited all the hospitals. But it is easy to see that that's such a big assumption, and it won't hold in most real-life scenarios because the sample space won't be the same for every hospital or every participant, right? So I would like to follow by showing you what a real BFL scenario looks like for a two-participant case. So we will actually have some samples that are aligned between the participants, right? This subset DA. I like calling it the classical limit because those are the samples that can be used by the classical algorithms for training and for inference. But we can also see that there are some data blocks that are not aligned between participants, right? So here the big question is like, can we somehow use this data? Can we incorporate the knowledge of this data to the training process? And what's even more important, can the active participant do the predictions of these non-aligned samples, right? So taking into account these main limitations or these main problems of classical vertical federated learning, our proposal or our approach has two main goals. So with our approach, what we want to achieve is flexibility and efficiency. Flexibility, why? Well, we don't want to be limited to the usage of aligned samples for training nor inference. And we do also want our approach to be efficient in the sense that we want to reduce the required communication rounds as much as possible. Because if this is high, there can be some issues in real scenarios when participants have communication issues. So how do we aim to achieve this, or how do we aim to tackle the issues of classical BFL? Well, with our approach, APC BFL. So in here, you can see the general overview of our proposal, which has 4 different steps, but I like dividing it into 3 main blocks. So the first block would be the first 2 steps that are the federated steps. We will see in a second how we do this, but the goal in here is to learn a joint representation of the aligned samples. And what's the most important part in here is that we require a single information exchange between participants, which is carried out in this second step. After that, the federated part is over, we can say. Because in the third step, what we do is we do knowledge distillation to transfer knowledge from a federated model to a local model. And then in a final step, we train the classifier. Here, it is important to mention that in order to train the classifier, we will use the whole data set of the active participant. That is, we won't be limited to the usage of aligned samples. Therefore, we are able to achieve the aforementioned flexibility. So being this a general overview, I would like to go a bit more in depth into each one of these steps so that you guys can understand which was the thought process behind it. Well, so in the first step, what we are aiming to do is we are aiming to learn the representations of the data of each participant. So for that, what we need to do is we need to train these encoders over here. So the question that we need to answer is how can we train these encoders, right? So we want to be able to train them without using labels. Why? Well, as I have said before, the active participant will have access to some labels, but the passive won't. And we wanted this first step to be identical for every participant. Because of that, we chose not to use labels in it. So taking that into account, the most logical approaches could be using contrastive losses or using autoencoders. Some people may think that we should go for contrastive losses because they are super popular in self-supervised learning, but it must be noted that our approach focuses on the tabular domain, and they aren't that well known for tabular domain. Because of that, we chose autoencoders. So basically, the idea in this first step is to train these encoders, but locally, without exchanging any information between participants. On that way, what we are doing is we are giving more weight to the local training and making the process more efficient. Once we have these encoders trained, in the second step, the idea is that every passive participant should send the representations of its aligned samples and only the aligned ones to the active participant. This one will concatenate them, and by means of another encoder, will get a joint representation of them. So, as we chose autoencoders to train these encoders of the first step, so do we in this second step. And G2 is nothing but the encoder of another autoencoder. So having this trained, the federated part is over, as I have said before. Because now what we do is we do a knowledge distillation process, where we somehow aim to transfer the knowledge from this federated model to a local model. And we do more precisely feature-based knowledge distillation. Why do we do it? Well, the goal is to guide the training of this autoencoder of the third step. Because this autoencoder will be trained using only the samples of the active participant, the whole dataset, the aligned and the non-aligned ones, but it will only see active participants' data. So how do we try to guide the training? Well, we try to guide the training with the following loss function, which depends on the type of data that is being processed by the autoencoder. So in case that the data point is not aligned, we don't really have any extra information about it, right? So the loss function is the reconstruction error of the autoencoder. But on the other hand, if the data point is actually aligned, that means that we do have some extra information about it. Which is that extra information? Well, the joint representation that we learn in this second step, which is a representation that gathers the information that every participant of the federated process has about that sample. Therefore, in that case, we have a compost loss function, which is the reconstruction loss plus the distillation loss. So here the idea is that on those cases where a data point is aligned, what we say is that, well, the autoencoder shouldn't only give a gut reconstruction, but it should also be able to generate a representation of the data that is similar to the joint representation of the second step, which is a much more informative representation. So what we argue is that by guiding the training of this autoencoder, G3, this encoder, is able to give us enhanced representations that have been enhanced by the federated process. So the final step is the most straightforward one. What we do is we simply take this final encoder and we get the representations of the whole dataset of the active participant, which can be seen as some alternative dataset. And using that alternative dataset, we train the final classifier, which can be any machine learning or neural network. So that's what we propose. So now I would like to explain which are the experiments that we have done and the results that we have obtained. Well, so we have done two different sets of experiments. We have used two different tabular data sets, and we have tested everything in vertical federated learning scenarios with two participants. The first set of experiments is the set of experiments that we do in a real BFL setting, that is, without fully aligned data sets. There, we do compare our approach with different baselines. Being the first one, a locally trained model, a model that the active participant will regularly train. Then the other baseline is another locally trained model, but in this case, we train this model not with the regular dataset, but with a transformed dataset. How do we get it? Well, so the idea is that we train the autoencoder of the third step, but we do not apply any sort of knowledge distillation. And once we have it trained, we get the alternative dataset and train the local model. So this is a super important baseline because this can be seen as an ablation study, because this will show us how effective the knowledge distillation process is. And then the final baseline is BFET trans, which is another state-of-the-art BFL method. Then in the second, and in here, we do generate different scenarios by varying the data partition. That is, by varying the amount of features that each participant has access to. And then in the second set of experiment, we do assume that the datasets are fully aligned, and we do also assume that the scenario is ideal in the sense that there is not any sort of information loss during the training process. And under that scenario, we compare our approach with vertical split NN, which is the first algorithm that I have explained. So notice how, when we assume that the datasets are fully aligned, the knowledge distillation process doesn't really make much sense. Because of that, we do modify our approach, and what we do is we train the classifier on the joint representation of those aligned samples that we learn in the second step. With this, what we do is we aim to evaluate the effectiveness of local training using those autoencoders. And in here, we do not generate different scenarios by varying the amount of features that each participant has access to, because the training and inference is done in a collaborative fashion. Here we do vary the number of aligned samples, which is equivalent to varying the dataset size, because the datasets are fully aligned in this case. So which are the results that we have obtained? Well, in the first dataset, which is Mimic3 in the real scenario, what we can see in here on the x-axis are the different scenarios, and in the y-axis we have the F1 score. We chose the F1 score because Mimic3 is a multi-class classification task without fully balanced classes. So the blue line shows the regular local model trained by the active participant. The purple one is the other state-of-the-art proposal. The yellow one is the ablation study, that is the local model that we have trained with transform data, and the other two curves, the green and the red, are the result of our approach. So what can be seen here is that our approach does outperform the other alternatives, but what's truly interesting to see is the difference that there is among our approach and this yellow line, because this is the difference that knowledge distillation is doing. Therefore, we can see that it is worth doing this knowledge distillation process and the federated learning part. Then in the second dataset, which is breast cancer Wisconsin, a binary classification task, what we can see is identical. Our approach does outperform the other alternatives, and there's especially interesting to analyze the difference that there's between our approach and the yellow curve. Then, when it comes to the comparison with split NN under the ideal classical setting, in the first dataset, Mimic3, what we can see in the first column is the dataset size, that is the amount of aligned samples. And in the last column, what we can see is the communication rounds among participants that were needed for the training process. So what we can see in here is that when the dataset is relatively large, split NN does actually have an edge over our approach. The performance is better, but it does require to exchange much more information. But when the dataset size gets smaller, that difference does also get smaller, and it gets to a point where our approach does outperform split NN while being much more efficient. Then, in the second dataset, breast cancer Wisconsin, what can be seen is that the results are pretty much equivalent in every scenario, but in the last one, where our approach outperforms split NN. So, being this the results, just to finish the presentation, I would like to make some sort of quick summary as final conclusions, and I would like to mention a couple of interesting future working lines. So, well, in this work, we have developed a new VFL method that requires a single information exchange. That is, we achieve that goal of efficiency that we have set in the beginning by reducing to the maximum the amount of communication rounds between participants. And we achieve that by combining local self-supervised learning, in this case using autoencoders, with a knowledge distillation process. And we also say that this approach is flexible in the sense that it is not limited to the usage of aligned samples for training nor inference. When it comes to the experimental results, what we have seen is that is that in a real BFL scenario, it does outperform other alternatives. And then when it comes to the comparison with vertical split NN, which has been carried out in an ideal classical BFL scenario that is fully aligned dataset and no communication issues when training, what we can see is that there are certain scenarios where our approach does get equivalent results by being much more efficient and flexible. Because even though we have done the comparison in this ideal scenario, our approach is not limited to it. When it comes to the future lines of work, there's a lot of work that has to be done still in the field of BFL, but closely related to our work, we think that it will be interesting to explore alternative representation learning methods because our approach does not work in the feature space, but it works in the representation space. So we think that by having better representations, the overall performance will be enhanced. And finally, we also think that it will be interesting to extend our work to scenarios where participants have, for instance, images instead of tabular data, or even multimodal scenarios where each participant will have a different modality. So that was all. Thank you very much for your attention. And now, if you have any questions, I will do my best to answer them. But also, here you have my email address. So feel free to send me a message. So thank you very much to the Flower team and especially Javier for inviting me here and giving me the chance to share our work. Thank you.
Okay, this was a great talk, John. Thank you for providing the details and also the ideas on how to take this work further. So while the audience thinks for some questions, I have a couple of questions that I would like to ask you. So the first one, which I wrote just as you were finishing your presentation, is, well, you are working with tabular data, but then the moment each client and the active and all the clients participating, the moment they pass their data through the encoders, then there is no, at least from what I can understand, there is no machine learning component that is specific to tabular data anymore.
That's it. Yeah, that's it. I mean, you are, at the end of the day, what you're doing is you are working in this, then share the whole architecture. So you mean in here, right? Like once you go through that encoder.
Yeah, once you enter into phase 2, everything is encoders. It could be machine learning modules and stages that could be perfectly used for other type of data that is not tabular data.
Yeah, that's it. So in here, just by adapting the architecture of these models in here, you could adapt the proposal to any other modality in principle. So you could work with images, for example, if these models are convolutional networks.
But do you think there would be value in, given that the data, it is known that it's tabular data, and there are so many forms of processing tabular data that work better than, for example, I'm thinking about, random forest or XGBoost. It works better in general with tabular data than passing it to a random CNN.
Okay, yeah, so that's the thing. I think that will be interesting in here, like in the final step. You are free to use like a random forest or a tree-based algorithm, XGBoost. You can use whatever. So the idea of our approach is to somehow be able to generate this enhanced dataset, which is beneficial for the final classifier. But then the final classifier, we do not limit that. You can use whatever you want. So you could do a grid search and find the best classifier. You could do your test, and you could just choose the one that performs the best.
Can you give some maybe brief details on what machine learning model, like the black box, which ones do you use?
Okay, so in our case, the results that we share in the paper are based on logistic regressions because we were aiming to do some sort of linear probing, like what's done when you evaluate self-supervised learning approaches. So, because what we were aiming to do is to evaluate the quality of this data set. But we have also done tests with trees and super vector machines, and we see that it does work as well.
Thanks. One other question. So you have here several stages, and as you were mentioning, once the passive clients have communicated the embedding back, they are out of the picture, but still there are 3 more stages. Have you considered doing steps, 2 to 4 end to end?
2 to 4 end-to-end.
End to
Okay.
end by that I
Yeah.
mean,
Yeah.
include the final labels and the black box into the distillation, for example, as well.
Yeah, I mean, that's actually something that we are working on currently when we are trying to adapt this approach to the image domain. We are working on something like that. But yeah, you could definitely adapt this and train it end to end. Yeah, like you could have a loss function that will be like the cross entropy of the final classifier plus some sort of distillation loss. Yeah, you could definitely do that. And that's what we are working on currently.
Very interesting. Yes, final question. Could you give maybe from the top of your head some real world examples where, taking into account also the unaligned data could be useful?
Yeah, I mean, I will say that not only useful, but it's a must. Because let's say that you have this setting, right? And let's say that you go for only the aligned samples. So you, as active participant, you never want to train a model that you can only use for a subset of your data. So you will never say a bank, okay, I can try to help you train a machine learning model, but you will be able to use it only with some clients. And the condition would be that client having a bank account in another bank as well. So because of that, it's actually a must being able to use non-aligned samples in order to apply VFL in real scenarios. Because in academia, yeah, it's just fine if you are limited to the usage of aligned samples and you can do some really nice stuff. But if you really want to use BFL in real world scenarios, you need to be able to use non-aligned samples as well.
Okay. Yeah, I mean, this sounds like a pretty convincing answer on why we should take a close look into your paper and implement algorithms based on that. So, okay, I don't see questions at the moment, so I think we can thank you once more for the fantastic talk, and we can proceed to Lucas' talk.
Thank you.
Thank you very much once again.
Thank you for inviting me.
And if anyone in the audience is interested in this work, to learn more, feel free to reach out to John.